All right, so we'll go ahead and get started today. Welcome to the Brucite Serpentine webinar. We're going to be talking about how to quantify brucite and serpentine minerals using ultra-high UV, vis, and IR spectroscopy for the carbon mineralization application. So many of you here today have already used this technology before. Maybe you are interested in this application in particular. There's a lot of you here who are new users and who are new to the application in general. So I'm hopeful that everyone here will learn something today. Now, we know that planting trees is a leading method of pulling carbon from the air, but it's not a permanent solution. When trees die, carbon is released back into the atmosphere. That's not so much the case with mineralization. When carbon reacts with minerals like brucite, new minerals form and that carbon is locked away for geologic time forever. So this process of carbon mineralization, it really has the potential for global impacts on Earth's temperature. It's happened before. The Earth cooled dramatically 25 million years ago after India crashed into Asia and uplifted that Tibetan plateau. So these newly formed Himalayas began to weather and erode, and that caused countless megatons of carbon in the atmosphere to be captured and locked away forever. So long story short, hard rock carbon removal has cooled the Earth before, and they can do it again. Now, according to the IPCC, atmospheric warming should be less than 2 degrees Celsius to avoid, serious consequences with climate change. So this goal can be achieved in the mining industry in part by reducing these CO2 emissions by capturing and sequestering CO2, especially from mine tailings, for example. So just to kind of give you an idea of how this is done, companies like CO2 Lock in Vancouver, BC, have developed a way to use mineral extraction technology to store and verify CO2 for geological time. So how this works is you've got a brucite-rich serpentinized rock, a lot of times being peridotite, where that brucite is going to be extracted, mechanically ground, stacked, and watered. And then a CO2 stream is injected into that stacked material, which is going to accelerate and maximize mineralization. So that resulting material, which comes in powdered form, can actually be repurposed. So we can use it for forestry applications, agriculture, road material, and other purposes. So let's talk about CO2 mineralization potential in minerals. So on a per mass basis, minerals carbonate in the following order of decreasing reactivity. Brucite having the most potential, then wollastonite, onto serpentine, and then finally olivine having the least potential. Now, the reason why we focused on both brucite and serpentine in this study is because in these brucite-rich serpentinized rocks, serpentine has been found to be the most abundant mineral there. So while it might not have as much potential as brucite, there's still tangible potential just with the sheer amount of serpentine found. Now, there's been extensive research done on this specific application at University of British Columbia's Mineral Deposit Research Unit that shows brucite outperforms all of these commonly used minerals for this application. And that's because it mineralizes that carbon quicker and it stores more. Not only that, it's found in large geological formations around the world, which makes this application a very important one. So on to the technology that we used. Again, I did mention in the very beginning, some of you here are senior users of this technology and some of you are just beginners. So I'm just going to kind of go through a average spiel of the instrument that we used and essentially what it does. So again, we utilized UV, vis, and IR spectroscopy as our means of technology for this study. Again, there's plenty of education for those who are beginners on this. I would keep in mind that the instrument that we are using for this study is the highest spectral resolution for a field portable spectrometer in the world. So some of you who may be beginner users might be using standard spectral resolution, which is going to be a lot less spectral resolution than what we used in this study. So we've used this type of technology in the mining industry for a while now, and it's a proven method. The utilization of the 350 to 2500 nanometer range of the electromagnetic spectrum, which you see here in the bottom right-hand corner. So this is going to, essentially come out of the remote sensing needs, as was the invention of ultra-high resolution field portable spectrometers, like you see with the ORExpert up here in the top right. So this technology has been used not only in the mining industry, but for other industries like remote sensing as well. So the ORExpert, the reason why we use this is because the ultra high resolution, which you get 1.5 between 350 and 1000 nanometers, and you get 3 and 3.8 in SWIR 1 and SWIR 2. This is going to give you about double the resolution than you would get with a standard spectral resolution instrument like the ORExpress, or some of you might have used the Halo or the TerraSpec before. This is going to give you, double that resolution. So you're going to see more features in your individual absorption features. So a feature that might be a singlet with, an ORExpress, TerraSpec, or Halo might actually be a doublet or a triplet if we look at the data with the ORExpert. And why this is important for the Brucite and Serpentine application is because we're actually able to better discriminate between these two minerals, which have extremely similar spectral absorption features in certain regions. And so, because this is a reflectance style measurement, so that means that we are going to be illuminating these minerals with light. It gives us a spectral signature depending on how those individual molecular bonds reflect back. So again, just to reiterate, for beginners, this is a surface measurement, so it is not going to penetrate beneath that top surface where that light is going to reflect off. So this is done by using an attached accessory that has a built-in internal light source, which eliminates the effects of that atmospheric water spectra, allowing for a lot more applications than just, ground truthing remotely sensed data. So in general, this really changes the way the exploration is done and how us geologists think, as it provides more instant information about these minerals, which is why we chose to use it for the CO2 mineralization application. So just to kind of give an example of what this type of spectral data looks like, if you look here in this plot to the right, here are just some example spectra of brucite, olivine, and serpentine. So all three of these have very distinct spectral signatures throughout the spectrum, and those are correlated to the molecular bonds of that mineral. So this is how we're able to identify and distinguish between different minerals and even alterations of those minerals. So just to kind of give you an idea of what we get. So I mentioned previously that with a standard spectral resolution instrument, brucite and serpentine do look very similar. But in this plot here, this is our ultra high resolution or expert data. And you can see with the brucite, you have got a lot more distinct detail, especially in this 1400 nanometer region. And so you will see later on in the study, the samples that we used, because they were mixed with a lot of different other minerals, having this ultra high resolution is going to be crucial in order to be able to pull this brucite region out. All right, so let's actually talk about those samples. So again, the company CO2 Lock, that is based out of Vancouver, sent us these powdered mixture samples. So our goal with this was to take measurements with the ore expert and identify the brucite within these mixtures. So we did take 5 measurements per sample in order to get a better overall reading of the mixture, because remember, this is a surface measurement. So you might be getting some areas of the sample where we might be seeing some of the other minerals rather than the brucite. And we also used our EasyID mineral identification software in real time to identify the brucite and serpentine. Okay, so here you're looking at a screenshot of that EasyID software I was talking about, where again, this allows us in real time to measure the sample, and we can compare that to a built-in library spectrum. So the blue line that you see here is our mixture sample. And the red line is going to be our library spectrum. So when it comes to these mixture samples, remember we have molecular bonds and minerals that occur throughout the entire spectrum. But in our case, we don't really want to see the dominant mineral. We only want to find the brucite, which is why you see the green region labeled A. So this is the region that we hyper-focus on with the brucite because of the additional absorption features not seen in the other minerals within this mixture of the serpentine, magnetite, forsterite, diopside, and spinel. So as you can see here, the software, you look up here, top right here, if you see my mouse, you can see that, our correlation score, we've got a 0.924 correlation score to a brucite. So that's a pretty good correlation considering how complicated of a mixture this is. So not only was it accurately identifying the brucite, but we were identifying brucite at a very low concentration range as well. All right, so we've talked about the identification part of it. Now let's move over to quantification. So the goal here was to take known concentrations of minerals, measure those samples with the ore expert, and then use our spectral data to create a quantification model. Now, in order to train that model to use for unknown samples, we need to use reference samples with known concentrations. So again, for this study, these mixture samples that I had mentioned previously had been tested with TGA and XRD analysis beforehand so that we could build a solid model to use and then test that model as well. So the type of model that was built using the spectral data is a partial least square regression model. For some of you who are not familiar with this, it's technically a machine learning technique that can solve both single and multi-label learning problems. So what are the steps to create a model? Well, first we have to start with the spectral measurements of those known concentrations of the brucite and the serpentine mixtures. So we had a range of 0 to 12% for the brucite and a 70 to 91% range for serpentine. So after the data was taken with the ore expert, we needed to do some pre-processing to the data. So that means outlier, noise removal, and some smoothing if needed. We then built the model using what's called PLS Toolbox, which you can see a screen grab of here to the bottom right. Some people choose to create their own models using R or even Python. So we actually partnered with a company called Eigenvector, which is a third-party software. It's essentially a plug-and-play type software where you put in on the X box here would be your actual spectral data, and your Y output is going to be your known concentration range. So once this model is built, if we click the green model button, this will spit out a model. But the problem is we never want to just immediately use that initial model that's built. You want to make sure you're optimizing this model. So we want to test this with some validation samples to ensure that the model is accurately predicting the brucite and the serpentine concentrations. So once you've finally got it optimized, working how you want it to work, we can actually export this for real-time prediction on unknown samples. So let's take a look at that. All right, so the left-hand part of the screen that you're going to be looking at is going to address the brucite data. Top left here, you can actually see the spectral data of the mixture samples that we were hyper-focused on for quantifying that brucite concentration. Bottom left here is going to show that PLSR model that was built using the data imported into the PLS toolbox. And you can see here the highlighted region, we do have a prediction R-squared score of 0.999, which is a fantastic correlation for quantification purposes. The top right is going to address that serpentine section. So again, you have your actual spectral data here. The bottom right is going to be that calibration. Mind you, I had accidentally said prediction squared, but this is the calibration model for the serpentine, and we have a 0.997 score there, which is also very good. So the idea here is now that we've got our calibration models built, we need to test these models. We need to see how accurate is our calibration model performing. So let's take a look at that. Let's start with the brucite. So here is a screenshot of the imported model that we built and also test data being used in real time. So if you look here on the left, you'll see that it gives real-time quantification as you take measurements with the spectrometer. And it's also using, its post-processing style being shown here. So we had loaded this data in after the fact and also tested it. So again, to the far right here is you've got your actual spectral data that we're testing that calibration model with. To far left here, where we have loaded that model in. And as we are either taking measurements or we are selecting measurements, it's going to give you that concentrated brucite. So our actual TGA prediction for this was 2.3%. We were able to get it to a 3.4%. So typically with this type of stuff, in this industry, a plus or minus 2% error is typically accepted. You also have to keep in mind, if we wanted to optimize this model even further, we probably could get this brucite concentration closer to the TGA score. But then again, you also have to remember how truly accurate is the TGA. So that's another thing you have to keep in mind. So on next is the serpentine. So again, to the left here, we've got that serpentine model imported. And you've got our concentrated 86.6%. The XRD predicted 81.7%. So, oops. So right back there in the money. I mean, we're right in that plus or minus 2%. So to the far right is that test data that we have for the serpentine. So again, just to kind of reiterate what I talked with about the brucite. Typically whenever you create these models, you're not relying on just one single source of technology for, your concentration. So who's to say that the XRD prediction is right on the money? Again, if we wanted to optimize these models even further, we could get this number, a little bit closer together. So just to kind of conclude what we did here and what the results were, you can see that the data taken with the ORExpert, it's a fast solution, compared especially for you hear who may be, waiting months and months, sending samples to a lab, waiting on results. The Ore Expert is a fast solution for that. It takes about 3 seconds to take a measurement. And the data that you take with the Ore Expert, it can easily be used for quantification. So if you are someone who is interested in creating these, quantitative models, model building with the spectral data, you can just use the concentration of those calibration samples to create that. You just have to keep in mind that, you do have model maintenance. So that very initial model that we create is not going to be the model that we use at the very end. So you have to constantly be doing maintenance on these things. Now, partially square regression, it really depends on the application, but typically PLSR is a good technique, especially using, spectral data for this. So with this application in general, Brucite and Serpentine, this worked good for us. And that final model that you build and you optimized, we can actually load that into acquisition software, and we can use that in real time, which is a huge help. Now, in terms of future work, this was more of a lab style study. So what's next is we actually want to start working on this for the field. And I would also venture to say, we would want to expand this into other, mineral groups as well. So with that being said, my email is here, lori.shelton@spectralevolution.com. So if you have any, questions, whether that be of this presentation, this study, if you have any questions on the instrument that was used, feel free to email me. Definitely follow us on LinkedIn. But most importantly, if you're going to be at PDAC here in a couple weeks, I will be there and we will have a booth. So if you'd like to discuss this or just come by and say hi, you're more than happy to. And yeah, if you guys ever, want to reach out, my email's there again. So thank you very much.